So this is schematic. So we suck the air, we take the air from the outside, and this is the fan, air inlet, and this is the fan section. Now the fan section, traditionally it has been a titanium, 6 aluminum, 4 vanadium type of material, pretty long, fan blades. And then lately, the engine manufacturers have gone to polymer matrix composites. They also are trying to put aluminum lithium for the fan because it's a very lightweight and high stiffness. And right below the air, below the fan, as the air comes in, we compress it. There's a compressor section here. This whole thing is the compressor section. Again, the front portion is all titanium, but as they go behind, it's all nickel. I mean, it could be nickel. The last few stages. Last 2 or 3 stages could be nickel. And as you can see, there are several stages here, number of stages actually. So the blades at the first are long, and as you go back, they become smaller and smaller blades. And there's actually a shaft that actually goes all the way across the engine. That's the important thing. And a lot of these things are sitting on discs, discs with roots. And then, so as soon as the air is compressed, we mix the air with the fuel, and we get the combustion. Now, that's very hot section, obviously, because the combustion is taking place. And once the combustion takes place, then it drives the turbine. Okay, it drives the turbine, and the outlet engines come out. Now, we can monitor the exhaust gas, exhaust. We can put a sensor there, and we can exactly tell what the temperature inside the engine is. So recently, the engines that are being flown in the long distance aircraft, the data is constantly being sent to the mother station, like Pratt & Whitney if it's Florida, otherwise Cincinnati if it's General Electric. So where the engineers are constantly monitoring, or at least they're not looking at it constantly, but they're getting the data. Data is being acquired constantly as how the engine is performing in different places, depending on the altitude and all that. So low temperatures, high temperatures, obviously. So here it's all like titanium. So today we're going to talk about the nickel base for this, and there's also a turbine disc. So that's where I will be focusing on. Like I said, why nickel, right? Nickel has a face-centered cubic structure, okay? And in general, the face-centered cubic materials have good ductility and toughness. They have enough slip planes, 111 and 100 direction. So there are enough slip planes available, so that makes them ductile and tough. So that's a good thing, right? At least at room temperature, that's a good thing. On the outer, it's a 3D electron transition metal, nickel. So you got some outer electrons that provide good bonding and also good cohesive energy. So that's just comes with it. Luckily, the nickel stays as face-centered cubic all the way from room temperature up to the melting point. There's no phase transformation anywhere. Like if you go to steel, you got the gamma, then you got the iron carbide, then you got the pearlite and all these things, different, and martensite, which is a different structure. And same thing with titanium, you got this beta alpha structures, hexagonal close pack, all these things. Luckily, nickel's is simple that way, in the sense that it's very stable, no structural transformations. And the next good thing is the rate of diffusion, nickel, the way it moves in the metal or at high temperatures, is very conducive to thermally active deformation, okay? Because if you want a material which is very stable towards creep loading, you want the atoms to diffuse slowly, because the high temperature creep is controlled by the diffusion of the atoms. So if the diffusion is slow, then you have a better creep resistance, okay? It will not creep quickly. So the cubic structure is essentially, as you see here, you got the, wait a second here, is this nickel? Yeah, this is nickel. So you got the aluminum, wait a second, this is the FCC nickel aluminum. This is the gamma prime structure. That's what I was thinking, it looks different. Okay, so there is a nickel, I took it from the periodic table. Let me go to the next one and then come back. I'm a little bit ahead of myself here in terms of pictures. I'll go back after this. So this is one of the key things for nickel alloys. It's not very hard actually, but when you see a nickel alloy, there are so many elements, right? Super alloys have so many elements that sometimes you wonder, how can I remember all these things? There's nothing to remember really. So there are several elements that have the same atomic radius as nickel. That's number one. And just like titanium, these elements, nickel, cobalt, iron, cobalt, nickel, chromium, moly, tungsten, ruthenium, and rhenium, they all partition into gamma, the austenitic phase or the phase-centered cubic phase. And because they have a similar radius, it's easy to put quite a bit in there because they go substitution, 1-to-1, same radius, right? And gamma is the continuous phase. That's the nickel. So like we said before, there is a nickel, okay? Like your magic carpet, nickel. And then you got your Ni3Al phases. We'll come to that. So these are all solid solution hardening elements. So they go into the solid solution and they give strength to according to the Hume-Rothery rules, they give strength to the nickel, okay? And then you have some elements like aluminum, titanium, niobium, I don't remember the next one, tantalum, they have a slightly greater atomic radius than the nickel, okay? And then these guys promote the ordered phase gamma prime, Ni3Al. Ni3Al, but sometimes titanium goes in there, tantalum also goes in there. But Ni3Al is the primary strengthening phase for nickel alloys, okay? And the volume fraction of these gamma prime phases can change anywhere from 10% to 90% even, 80%, 70% on this, you know, okay? So now let me go back to the previous slide. So this is our gamma prime microstructure or crystal structure, okay? Crystal structure, where you got these nickel atoms on the faces of the face-centered cubic and aluminum atoms on the corners. So face-centered cubic, aluminum atoms on the corners. So for every one of these cubes, you have one aluminum atom. 1-8, 1-8, 1-8, 1-8, 1-8. So 8 1/8 contribution to because you have a lattice up on top, this way, that way, that way, this way. So on this way. So each aluminum atom contributes 1/8. You have 8 corners, so 1 atom. These nickel atoms are on the faces. So this face shares 1/2, the top face shares another half. So you have 3 nickel atoms total, okay? So 4 atoms per structure there. So that's the gamma prime structure, okay? Nickel and aluminum. Yeah, Ni3Al, 3 atoms to 1. So we already said these are aluminum stabilizers, solid solution stabilizers. These form gamma prime. Now this is the most important thing, that the gamma prime phase is also FCC, luckily. It's also FCC. So the gamma prime is coherent with the gamma. So the atoms just match up. So the nickel atoms and this gamma 3Al, Ni3Al phase match up pretty well, okay? And then as the temperature goes up, these precipitates can become larger and they can lose their coherency eventually, right? Okay, so that's gamma prime, right? In gamma prime, you'll have primary gamma prime, secondary gamma prime, and tertiary gamma prime. We'll worry about that later, okay? Just gamma prime. In some alloys, you can also have gamma double prime because it gives you more strength. But that only happens when alloys have a lot of iron in them. Not a lot, means it's not iron base. It's still nickel base, but iron in it quite a bit, and niobium. When these two elements are present in a nickel-based superalloy, there is a very good potency for gamma double prime to form. That gamma double prime gives you more strength. Okay, so gamma prime gives you some strength, Okay, so these solid solution elements give you some strength, solid solution hardening. Gamma prime gives you some strength, and you can even push it further by using this gamma double prime. And look what, even the, okay, that's fine. Actually, okay, that's fine. Then you have boron and carbon. I said there are not that many elements to worry about, but still, boron, carbon, and zirconium, just like many other alloys, they go to the grain boundaries, okay, forming borides and carbides, and they will reside at the grain boundaries, as borides and carbides, and they will, control the grain size a little bit up to some extent, right? And then you have some junk, but we won't talk about right now, okay. This yellow box actually goes to the last slide, but I could not fit it in. So in reality, this box should not be there. So let it not confuse you. This belongs to the previous one. It does not belong to the gamma double prime, okay? It belongs to gamma prime. So between the gamma prime has got a lattice parameter. So does the nickel has got a lattice parameter. There's a misfit between the two because they're not going to be exactly, on top of one another. There will be, but it's not like zero misfit. There is a little bit of misfit, which is given as the lattice parameter of nickel minus lattice parameter of gamma prime divided by the sum of the two. Lattice parameter of nickel plus gamma prime and multiplied by 2, okay? So misfit depends on partitioning of solutes in gamma and gamma prime. Because anytime you put a solute, the lattice parameter is going to change a little bit, you know what I mean? Especially if although the atomic radius is pretty close to each other, but it's not exactly, depends on how exact you want to get, Okay, so that's the main thing. So there is a misfit. That has got some implications. We'll talk about that in a second. So like I said, this is about gamma double prime, like we said. If you have iron and niobium in your materials, you can form gamma double prime. You can have more strength. When greater strength is required at lower temperatures, example turbine discs, these can be strengthened by using gamma double prime. So turbine disc is one of the key elements of this whole turbine structure, okay? Because there has been one accident some time ago, I don't remember exactly, 88 or something like that, where the turbine disc blew up, it ruptured, okay? It could be minus or plus. Yeah, yeah. Is that what you're asking? Yes. Yeah.
A is not equal to B, that C is not, that case, is it common?
You mean C? Where is C coming from?
That A, B, C.
It's not hexagonal close packed.
So, okay.
Face centered cubic.
If A and B are not equal?
A and B are not equal. They are equal. The lattice parameter, this is lattice parameter of gamma, which is nickel. This is the lattice parameter of the precipitate. Yeah. So they won't be equal in that sense. Yeah. Right. Okay.
It's common for any FCC system, isn't it?
Yeah. It's common for any SVC system. If you take aluminum lithium alloys, where do you have Al3Li, which is L12 precipitate, pretty much the same as Ni3Al. People have been asking this philosophical question for a long time, that why does Ni3Al stable for such high temperatures, and why not Al3Li to those temperatures? Because they both are L12 structures, they both are ordered structures, but one remains way stable to very high temperatures, and the other one does not. Nobody knows the answer. So there is another fundamental problem for you to solve in the future, right? Okay. I don't think they know. Here is the gamma double prime structure, which is a body-centered tetragonal structure. So it's got a square base, but this length is longer, okay? The length is longer. So you have, so you can see A, B, and now it's a C. This is longer, body-centered tetragonal, just like martensite in steels, right? I think so. Yeah. So that's the thing. Yeah, but like we said, it occurs when niobium or vanadium are present, then you have gamma double prime coming up. So the Inconel 718, which is used very often everywhere, does contain the niobium and iron, Inconel 718, okay? And the gamma double prime particles are thin formed disks, and they also have the same coherency as gamma prime, okay? The 111 slip planes the 111 okay, here okay, I didn't type it right. It'll be just like the previous one, okay? Just like the gamma prime. 111 slip plane is the same as the 111 slip plane, and 110 direction is the same as 110 direction. Okay. Now, we are taught, when we take the first course in the metallurgy, we are taught about these strengthening mechanisms. And we know there are 4 main strengthening mechanisms, right? Grain size. If you change the grain size, if you make it smaller, the strength will go up according to the Hall-Pitch relationship. Then we talk about substitutional solution hardening, right? Then we talk about work hardening. And there's a 4th one. Interstitial hardening, substitution hardening, work hardening, grain size hardening, and there is one more that I'm forgetting. Huh? Yeah. Okay. Yeah. Okay. So there we are. So the first one is the grain size strengthening in the case of nickel-based superalloys. The problem with nickel-based superalloys is, I put down here, keep in mind that it's tough to control the grain size of nickel-based superalloys without changing the volume fraction of the gamma prime. They're intimately related. See, as soon as you get to engineering materials, things are not that simple, like nickel aluminum alloy or something, but it's a complex alloy. You got nickel, aluminum, and so many different elements, so suddenly the game is a little bit more complicated. So if you want to change the grain size, you have to understand that the volume fraction may also change, and we'll talk about that just in a minute, why it is so, okay? Okay, morphology of carbides and borides, and that's okay? Okay, so we said that the Ni3Al is an ordered phase, okay? It's an ordered phase. And the order actually stays for a very high temperature like that, right? I didn't bring a transmission electron microscope picture, but I'm going to describe and see if I can describe, okay? When the dislocations cut the Al3Li precipitates, they're shearing the Al3Li precipitates. There is my first dislocation that's moving in the nickel. So this is my nickel matrix. This is my nickel. And here is my Ni3Al, right? Ni3Al. I'm going to just put something like that, even though they are actually cuboidal. They're like cubes, actually. Well, they can be spheres too, but this is the most common. So when they're coming like this and they're going to cut, what happens is the dislocations do not move as single dislocations. They move as pairs. That's one pair. There's another pair coming behind. So as soon as the first dislocation cuts this precipitate, it creates something called as an anti-phase boundary, APB. It's very involved, so I thought I would not get into so much details. So as soon as it creates, so let's do this for a second. So there is my top part of the particle, and there is my bottom part of the particle. It has been cut, okay? So when you cut, there is this interface that has just been created. It's called as an anti-phase boundary. And this guy gives resistance to the second dislocation. It does not allow the second dislocation to just come and move. The stress has to go up before it goes and cuts, before it goes and does the same thing. That's a very serious mechanism, a strengthening mechanism for nickel alloys, nickel superalloys. Okay, it's called as order strengthening. Order strengthening that gives rise to at least 400 megapascals by itself. That's a lot of strength improvement because nickel already has some strength. Nickel aluminides, they are giving you something, but this order strengthening is giving you 400 megapascals, which is actually much larger than difference in modulus, right? Modulus differences, stacking fault energy, okay, which I have described here a little bit, interfacial energy, and R1 strengthening. So this order strengthening is higher than most of the contribution from that is a lot more than every other strengthening mechanism. So it's a dominant strengthening mechanism. So this anti-phase boundary, creation of the anti-phase boundary, and the dislocations moving in pairs and doing this whole phenomena is the main thing about, what I would say is very different from every other alloy almost in the alloys that we have known. This movement of paired dislocations, the first dislocation creating the anti-phase boundary, and the second dislocation feeling this obstacle, this potential, this barrier that it has to overcome is very high, okay? So anti-phase boundary creation and strength through it, okay? So that's pretty dominant thing, which everybody should know when we are talking about nickel-based alloys, okay? Why are they so, if they have coherent precipitates, what is so different? Like when we talked about Al3, when we talk about other materials like aluminum alloys, simple aluminum alloys, which are coherent precipitates, if we have coherent precipitates, if the dislocations are cutting the shearable precipitates, we don't see this dislocation pair movement. It only happens here, okay? Okay, stacking fault energy I put down here. Okay, we talked about stacking faults the other day, but I just wanted to put the stacking fault energy strengthening mechanism for nickel alloys in perspective. I want to connect the two now, okay? So what we said was, if a material has a low stacking fault energy, that means the dislocation can split up into two parts. So you have a dislocation. If you have a low stacking fault energy, you can split up the two dislocations. That's one point. The second point is, we also said that stacking fault energy, low stacking fault energy, is also one-to-one correspondence with planar slip. So if you have a planar slip dislocation movement, or planar slip dislocation happening, then you have low stacking fault energy. You can conclude that it's low stacking fault energy, okay? So when we are dealing with this nickel-based superalloys, the contribution from stacking fault energy that you see, the contribution of stacking fault energy to the yield stress that is manifested as enhanced planar deformation. I was going to say for a second enhanced plastic deformation. It should not be. Thank God, I didn't mistype. This is correct. It's enhanced planar deformation. So low stacking fault energy gives you enhanced planar deformation, but planar deformation does not necessarily mean ease of movement of dislocations on the slip plane. No, it actually means more resistance to dislocation motion. That's something very, very important, because I just want to make sure I did not convey the wrong meaning the other day, so what we said was, if you remember, we can even put this in the context of fatigue crack growth or anything like that, right? So we said, okay, here's a crack tip, here's a slip plane, there are some precipitates here, okay? And the dislocations are coming, they're coming, and they're cutting this thing. So this is planar slip. It's on one slip plane. But if you have a cross slip, that could be like that. Okay? But in this single slip plane, that planar deformation also means that there is a more resistance to the dislocation movement in general. Okay? So the next dislocations that are coming, it's not that easy, even though they're moving in the same slip plane, but there's a little bit of resistance. This dislocation is going to put some resistance on this guy. He's not going to just come and let him sit next to it. That's the way to look at it. Okay? So these are some very, excuse me, important strengthening mechanisms, right? Little bit more on, this is a terrible cartoon I did this morning. I have to clean this up before I submit it to Professor Arora. Okay, I just did this quickly, just to illustrate my point here. So gamma prime solvus is approximately 1050 to 1200 degrees Celsius. For just like you had the beta trances for titanium alloys, we have a gamma prime solvus for the nickel-based superalloys. If you go above the gamma prime, the precipitates will dissolve. If you remain below the gamma prime, they will all remain there. But of course, the dissolution just does not take place at one temperature like anything else. It's a window of temperature, okay? So, but for many alloys, because there are so many compositions, usually what we found is the literature shows that about 150 degrees range, most of the alloys have their gamma prime there, okay? So when you go below the gamma prime solvus, obviously, not all of them are going to be, actually none of them will be dissolving. They're going to stay there because you're below the gamma prime solvus. If you go above the gamma prime solvus, they will start to dissolve. The gamma prime, elimination of gamma prime through dissolution, okay? So here, on the pinning effect, resulting in coarser grains. So super solvus, this is what we meant when we said in the beginning that it's tough to control grain size in these alloys without affecting the gamma prime volume fraction. This is exactly what we mean. So in the as received material, I've got a grain size and I've got a gamma prime volume fraction. So when I take it to, when I keep it under the gamma prime solvus, that's fine, no problem. The gamma prime remains like that, but the grain size is also not going to change a whole lot. But as soon as you go up above the solution heat treatment, super solvus, the gamma prime is going to dissolve and the grain size is going to get bigger. So they both are having an effect, okay? And the longer you keep there, the coarser the material, the grain is going to get, okay? Because once the gamma prime is gone with the solution, even if you keep it there for a longer time, nothing is going to happen with respect to gamma prime, but the grain size will keep on increasing. So there is a relationship there, how you manage, depending on what is the property that you're looking for, the ultimate performance, that you're looking for, there it is, okay? And I also said that gamma prime could be primary gamma prime, it could be secondary gamma prime, it could be tertiary gamma prime. Okay, so I said here, these are all approximate numbers. These are all approximate number. Aging at 700 degree results in the tertiary gamma prime coarsening. So here I've done not a good job at all. This is terrible, but that's the best I could do. The other thing, maybe I should have drawn on a piece of paper, took a picture, and then probably put it there. That would have been easier. This is terrible what I did. So here are the grains, the large ones on the grains, okay? And here is my gamma prime, okay? These are the gamma primes. These are secondary, oh, I'm sorry. These are the gamma primes sitting at the boundaries, gamma primes. Here are the secondary gamma primes, and the small ones are tertiary gamma primes, okay? So these gamma primes act as a pinning point also for the grains because they're sitting right there. Okay. I'll go over some of these things later on again. Shinde, huh? Yeah. So these, it doesn't come this far. So if I go to above this 1050 to about 1200 degrees C, for instance, these grains will get larger, these hexagons, they will coarsen, okay? And these precipitates by then will also dissolve. These will dissolve, the one that are sitting at the boundaries, they will dissolve, okay? This is not dissolved, I put down, if you're under the solver's temperature. As soon as I go above this, these guys are dissolved, the gamma primes, and now there is a chance for the grains to get bigger, okay? And the secondary and the tertiary may also dissolve, but when you quench it, or when you come back from the gamma prime solvers, either furnace cool or air cool, you can do both ways. And then if you do the aging, then you start to precipitate again everything, okay? So you can start to precipitate, just like anything else.
So when it goes for a very long flight,
it goes for a very long
flight, so the temperature is increased. So there is probability of aging?
No, you will not probably go
Up to 700.
but you will see what you're saying in a few minutes. Yes, you will stay below the aging temperature, but when you go above it, there will be changes in the microstructure. Absolutely. If you go a long time. Yes, absolutely. Yes, absolutely. Yeah. Absolutely. Huh? Yeah. Something else? Shinde, am I okay? Yeah. So, oh yeah, this is just like aluminum alloys, for instance. When we are talking about aluminum alloys, we are so that is my solution heat treatment for aluminum alloys. I mean, the language is different, that's all. Every alloy has got its own language, unfortunately. Well, unfortunately. Actually, it's good they all have different languages. Solution heat treatment we use for aluminum alloys. And we keep the alloy here, let us say 500 degrees C for about 1 hour. And then we quench in water, okay? Quench it in water. And then there is also thermomechanical processing. Yeah, okay. We can do thermomechanical processing here also, and then we age it. Aging. That's aluminum alloys. You're doing a corresponding thing here also. Here what you're doing for nickel alloys, super alloys, we are doing above or below the gamma prime, okay? Here the solution heat treatment is at one temperature. In the nickel-based superalloys, we are going either above gamma prime or below gamma prime, depending on the application. I'm going to show you what that is just in a minute. And then you furnace cool or you slow cool, faster. Oh, furnace cool is slow cool. Air cool is fast cool. And then you age it. So, and in titanium, we can also put one for titanium here, beta trances, right? Bhanumat garu, yeah? Beta trances, and then we can do similar things. Furnace cool, air cool, and all those things. So I want you to, I want some of these young guys in this room, I want you to not, I mean, we can do it too, but the young guys especially, try to see the similarities between alloy systems, processes. There are a lot of similarities. Only thing is the language is different. But there are similarities between aluminum alloys, titanium alloys, nickel-based superalloys, you know, steels. What are the similarities? What are the differences, right? So try to digest that kind of information. The more you will think about those things, the more you can start to connect the dots in science, always, okay? There are patterns everywhere. There are patterns. So it is the pattern that you have to recognize, okay? Like, so very similar, you see what I mean? Similar. So when you're reading things, try to put down those things, okay? I'm not going to lecture you, I'm just giving a suggestion. Okay, so For a moment, let's look at variation of yield stress as a function of temperature. Now, this is very, very unique. Why do I want you to take a look is because this is a very unique behavior of nickel-based superalloys. Now, this is a particular graph that I took for 20% of gamma prime, okay? Now, this type of a graph you can get for 40%, 60%, 80, 90% gamma. Each one of those will show approximately same behavior, but there will be, qualitatively it will be the same, but quantitatively they will differ, okay? So the pattern is the same, but quantitatively the numbers will change. For this 20% volume percent of gamma, look at, so this is your curve for yield stress as a function of temperature. This is the temperature going up. You will notice that this is all pretty much from here, 800 degrees C, not a dramatic fall, right? I can average it out and say that this is pretty constant right there. And then the bottom falls out. As soon as you reach about 700, the next 300 degrees it falls out. If you take alloys, specific alloys, with high volume fractions of gamma, this can actually go up like that and then come down. This is a totally different behavior. For a minute, imagine, I should have drawn that also. If you imagine that, this hump actually being higher, that's totally different from the behavior of other materials, right? That is reversible, I mean, it's not reversible. A behavior where the stress is going up, the yield is going up with increase in temperature, which is not usually the case, right? So that's something, okay. How the strength is insensitive to temperature, that is for this diagram, but like for this alloy. But if you had different alloy, it could be like that, okay? So enough said about that. And this is about 1,000 times stronger than nickel. 1,000 times stronger than nickel. So as soon as you start to put alloying elements, you're already receiving the benefits, even at 600 degrees Celsius, 1,000 times the benefit. I mean, the benefit is 1,000 times the yield stress of the 700 megapascals at 600 degrees Celsius is pretty good actually, quite good actually. Yeah. Okay. Yeah, I said here, depending on the volume fraction, this peak can be higher at 800 degrees Celsius or, yeah. Okay. Let's go back to that subsolvers and supersolvers that we just mentioned. Can everybody see that? Huh? Okay, can everybody see that? Let's go to, first of all, the supersolvers maybe here. You can see the grains very clearly. And all those gamma primes, see these gamma primes here, all these particles, they all have been dissolved basically at the supersolvers, like we said. So this is about a temperature of, let us say, anywhere from 1100 degrees Celsius, about halfway. So if you take your material about 1100 and keep it there just for a little bit, all the precipitates have gone into solution, just like a solution heat treatment here on the, on the board, just like a solution heat treatment of aluminum, right? All the precipitates have gone into solution, solid solution, and you can see the grains. These are the grains that are going to get bigger if you keep it there for a longer time. Okay. And here there are gamma primes. You can see subsolvers, you can see the gamma primes. I'll come to the other ones a little bit later, sorry. I have to do this. I should have put this graph here. So what is so big deal about this coarsening of gamma prime grains on this gamma prime precipitates? I mean, the grains, bigger the grains, because look at this. If you look at the properties and grain size, this is a general behavior, right? Let's look at the tensile strength, right? As the grain size gets larger, your yield stress goes down. That's no surprise, Hall-Petch equation, no problem. For creep, we all know that we need a larger grain size. So if you want only from a strength application, you are probably okay doing your heat treatment below the subsolvers. Okay? But if you want creep, you want large grains. You want to put it above the supersolvers because you want large grains. If you want crack growth, large grains are better for crack growth. There is. So creep and crack growth go hand in hand, pretty much, throughout the literature. Take a literature look one day when you have time, or not one day, a couple of months it'll take you. If you look at the literature of crack growth crack growth and creep, if you're trying to look at the effect of grain size, in general, that's what you will find. But unfortunately for engineering alloys, it gets a little complex. Even for aluminum, the answer is not so straightforward because it is overshadowed by other things. Okay? But that's a rule of, that's pretty much. The LCF life and the yields and the strength go together. Okay? Smaller the size, better the low cycle fatigue life. Okay? So, this is something I don't think I've ever clarified. Let me see if I can clarify this. This is my high cycle fatigue curve. High cycle fatigue or stress control fatigue. It's too small a word, you can't see from there. High cycle fatigue or stress control fatigue. And we said here that the curve is like this, endurance limit, right? Sigma, some sigma, number of cycles to failure. There is my endurance limit, right? And we said here it could be 10 to the 7 cycles most of the time, except under special circumstances. And those circumstances are for engine alloys, like nickel-based superalloys, you want to go higher. 10 to the 9, 10 to the 10, because that machinery, the turbo machinery is rotating so fast, it puts on cycles just like that. So this 1 million, 10 million is not enough. You have to go higher, 100 million, 1,000 million, right? So there is your endurance limit. Sometimes people refer to this low cycle fatigue life, this also. Because this is low number of cycles, they refer to these also as low cycle fatigue. Okay? Because they are very small in number. So let us say this is 10 to the 3, that's 10 to the 7, 4, 5, 6, 7. Yeah? So this is also referred to as low cycles because we're talking about 10 to the 3 to 10 to the 4. But the other low cycle fatigue definition, unfortunately, is like this, that can confuse you in the literature, is those hysteresis loops where your material has seen this much deformation. This is your plastic deformation from here to here. Delta, cyclic plastic strain. This is actually low cycle fatigue. Okay, let's see what time it is. I want to do one thing before we even think of, we're not going to break right now. I'm just telling you. Okay. I wanted to write the differences between high cycle and low cycle. In the high cycle fatigue, when you're doing the test, the material is below the yield stress. You're below the proportional limit. No dislocations are being emitted on a macroscopic scale. High cycle fatigue is stress control fatigue, which is below the yield stress of the material. If you make a column on the right side, low cycle fatigue, the stress, well, is a strain control fatigue. Low cycle fatigue is strain control fatigue in comparison, in opposition to this. Strain control fatigue, where the material is above the yield stress, above the yield stress. So in applications where you're expecting the material to yield a little bit, above the elastic limit, this is what you use, a strain control fatigue, to see how many cycles it's going to take to fail. But if you're below the yield stress, that's what your application is, then you do this high cycle fatigue test, okay? This width of the loop gives you the plastic strain. The tip to tip gives you the total strain. Just, yeah, that's okay, yeah. The tip to the tip will give you total strain. So since I'm doing a strain control fatigue, I can set the machine to any strain you want to. So maybe you want just about the yield stress, so 0.3% strain. 0.2% is your yield stress. So 0.3%, you can tell the machine, hey, cycle the specimen only between 0.3, plus 0.3, minus 0.3, and tell me how many cycles it takes to fail. It will tell you that, and also it will tell you the peak stress, because this is your stress axis, and that's your strain axis. So from a stress slide, from a test like this, you can find out how many cycles it takes, like this type of a low cycle fatigue test. You can tell how many cycles it takes in order for the component to fail under cyclic strain conditions. And you can also see what will be the stress. You can either take half the cycles or saturated. That we can go over that also if we have time. We'll have time. But I want you to write down this figure, because this is an important, or we'll give the notes. Professor Arora is going to make copies of all this. But this is an important graph from an application point of view, right? If you want good fatigue crack growth, if that is what your driver is for your design, fatigue crack growth, you don't want to be doing something like this, right? You want to be doing something like that. But maybe you want a balance of this and this. So maybe you want to make a compromise somewhere, right? So here, stress corrosion cracking is not important. It's the hot corrosion. Somebody brought up, I think, the other day, Professor Kumar brought it up, Dr. Kumar brought it up. The hot corrosion is important because the component is high temperature. So hot corrosion is more important, right? Okay, I didn't drink my water today, huh? So let's go back to where we were. I should have moved that right after this or before this, okay. So here we are, right? So there is your grain size. You want to control the grain size, go above the supersolvus, you know. So here are some experiments, actually. The triangles, can everybody see these triangles from the back? Can you see the triangle? Okay. So the triangles, the triangle means better fatigue crack growth resistance. Again, the language. We all mix up the language so many times. That is better fatigue crack growth resistance. The lower curve is always better fatigue crack growth resistance. Also, some people will say lower fatigue crack propagation, lower FCP, slower crack growth rates. Okay, same thing. They all mean the same thing. It's like Marathi versus Hindi versus Telugu or whatever, you know, different languages. We're all talking about the same thing, but different languages, you know. So we have to learn those languages. And here is the subsolvus. So you see, larger the grain size, supersolvus gives you larger grain size. So the crack growth resistance is better. Just what we saw on that schematic. Larger grains will give you better crack growth resistance. So let us say you have a grain size and it's giving you this crack, somewhere over here, crack growth resistance. You measure the grain size in your optical microscope. You go above supersolvus and increase the grain size and see what kind of crack growth rates you'll get. Most likely they'll get better. Better means down, okay? So good example right there, okay? The other observations that people have made is that when the crack growth rates are down like that, okay, below this thing, They always find, these are all same magnification. They always find this crack growth going very tortuosity, crack path tortuosity, or crack deflections. It's not intergranular, by the way. It's not like following the grain boundaries. No, it's a transgranular. It's actually, okay, oh yeah, I got the fracture surfaces right there. That's a transgranular. And when it comes to subsolvus, the crack front is pretty straight. The crack direction, or the crack profile rather, is pretty straight. Obviously, this will give you a better resistance to crack growth because it's zigzag, zigzag, zigzag. More energy involved. You can think about it like that too. Or if you want to think in terms of mechanics, you need a higher crack growth driving force to drive the crack from here in an angle like that. Uphill, it's going uphill, you know. It requires more stress intensity to drive it, okay? And that's how they're derived actually. Is it in focus, this one? Is it in focus? Okay. See the distinct fracture surface, okay? Completely different. This branched cracks always looks like this. Crystallographic, stage 1, they're the same thing. Stage 1 crystallographic cracking. This is stage 1 crystallographic cracking. We should write a dictionary on this whole. Let me erase this. Okay, I'm going to draw a line here. Okay, I'm going to say here better fatigue crack growth resistance, better FCG resistance. Let us summarize what we're talking about. Not so good. FCG. This also means same as, huh? Oh, you guys. Same as faster crack growth, oh, slower crack growth rates. Slower FCP, faster FCP. Number 2, well, you can put this number 2 if you want to, doesn't matter. This is same as, right? Better is always associated with zigzag crack propagation. Much planar. The crack growth stays in the same plane almost. Huh? So this is also called as crystallographic crack propagation, also called as stage 1 crack propagation. And the reason why they're called like this, we'll go through these things. Maybe not with respect to nickel alloys, then we will be diverting, but we will take one of these afternoons and go through these things, a little bit more elaborate. This is non-crystallographic. There's nothing here to define, crystallographic like this one. You can really see, right? Actually, is it focused? Yeah, okay. This is stage 1. This is not actually given any stage. It's not stage 2 exactly. Well, let us say well, it's more like stage 2. More like Paris regime or something like that. More like stage 2. And also let's put down here that we will compare separately. Because that will be like planar slip alloys, non-planar slip. Okay, we can do that also. Like if you take aluminum alloys in the underage conditions, it will be planar slip. They will exhibit these things. In the over-aged aluminum alloys, where the slip is more multiple slip, cross slip, this is what we will observe. So just, they're all, they all, at the end of the day, there's all unification is there. Make sense? We'll go to the next one. Yeah, I wrote down again, I think I just kind of summarized it a little bit, exaggerated it. Fatigue crack propagation. Supersolvus, supersolvus heat treatment is better than subsolvus for fatigue crack propagation. That's what we just saw, right? So supersolvus is better. It's below this line. This is better. Slower growth. So for a given DADN or for a given delta K, if I'll draw a line like this, for a given delta K, this crack is faster than this one, right? Or if I draw a line like this, for the same DADN, I need a higher delta K to drive the crack compared to this one. So you can look at it either way, right? So it's a general graph. Supersolvus heat treatment is better than subsolvus for fatigue crack propagation. Results in, well, actually, I was looking at some literature. So this is order of magnitude. It could be more even, well, maybe not more, but just about that, okay. Air cooling after solution heat treatment results in an order of magnitude increase in fatigue crack propagation, as opposed to furnace cooling. Okay? Air cooling is always faster. That means the particles cannot grow too much. There's no time. Smaller particles obviously will give rise to,
Are you doing some forced cooling also? Forced air cooling also?
Forced air cooling?
Are you doing forced air cooling?
Yeah, we can do forced air cooling, again, depending on what we want, sure. Yeah. Again, if you want a faster cooling rate, like the sir is saying there, Professor Chandra is saying, hey, go and use a forced air cooling. Don't quench it, do forced air cooling. So in this particular case, particle size decreased from 250 to 170 nanometers. Very small particles, all these things. That's not a small decrease, by the way. That's an average number. If you take 100 readings or 110 readings, there will be a good Gaussian distribution. You'll be able to see the distribution. Should we take a break here, or do you want to just stretch for 5 minutes, or do you want to keep going? It's up to you. How many want to take a break? Okay. Yeah, we'll take a break, 5 minute stretch. I'm okay, 5 minutes, yes, 5 minutes, yeah. Huh? I'm okay, but just.
Good morning. Actually, I had come to listen, and I'm finding in a situation that I am going to speak on something, right? I'll be speaking on something called as thermal barrier coatings on any super alloy, just to enhance the life part of it, and try to see we do certain types of coatings on the top of it. Coatings are done by means where any particle is heated and accelerated onto a prepared surface to see that that layer is being formed on the top of it. As far as your turbine is concerned, what we do here, this part which are subjected, the function of the coating is to technically reduce the amount of heat that goes to the waste material, and maximum possible using a zirconia, yttria stable as zirconia, we can reduce the temperature by about 232 degrees centigrade. Sure. Sure. So what happens? How is first, I mean, I would not go much into the detail of how the coatings are being done. We do it practically at our workshop here in Jata, and we also have a facility at LD College where we do it. What we do is, these particles of a very specific size are heated and accelerated onto a surface which has been made conducive so that they can stick there properly. And the thermal, I mean, they have also a bond coat which is applied, which is amcrolis, which does allow a very slow gradient of heat to be transferred from one end to the other part of it. So I'll just write it down here. Just a minute. The particles are sprayed. The important thing there is, first is a bond coat. The bond coat allows a transition in such a way, it's a metallic coat, so that from metal to ceramics when we go, the thermal expansion of coefficient does not affect and the coatings can peel off. All the turbines that you are seeing here are technically given a coating on the top of it just to enhance the life. The function is, as we mentioned, maximum reduction of temperature by 232 degrees centigrade. That means a super alloy which has been made in a particular way will be subjected to a lower temperature, because of which the life is much more enhanced. As far as the coatings are concerned, I mean, I don't know, are you familiar with how the coatings are being done? Not yet, okay. What is this done is, a powder feedstock is taken, it is heated to a certain temperature just near to the melting point of it, and then projected at a very high velocity. So two things, the kinetics which push the material, the thermals which also allow the sticking to take place. So the basically layer by layer, splat by splat, a coating is taking place, and a coating reaches a certain thickness. There is a level to which the coating thicknesses are being measured. So we give that coatings whenever they take care of erosion, they take care of the corrosion, and they take care of the temperature which goes to the base material, allowing it to remain stronger even at those elevated temperature. The difference why this is being done is that the fuel efficiency of an engine directly depends on the temperature at which the air injection takes place. If you see in a turbine, the compression takes place in a ratio of 1:30. Because of that very high level of compression that takes place when it comes here, the jet engine itself has been made in such a way that the force is mitigated. Otherwise, it's like a candle where a very high amount of air is coming in, extinguishing it. Just not to happen, they have different types of holes through which the flame does not extinguish, and then the flue gases which comes here are coated at this junction just to prevent the effect of the temperature coming. Are we clear? Anything more that you would like to ask, I can talk about it, because this is totally unscheduled, so I did not know what to speak about.
No, that's great. Can you just talk about the thermally chrome oxide, TGO, right after the barcode?
Okay.
So you have the barcode, and then you have the thermally chrome oxide, and then you have the TSK residual. There are three things. So,
the first splat that is formed is that of amcroly, M-C-R-A-L-Y. Microly they call it, where M stands for either Fe, nickel or cobalt. This is the bond coat. They are applied by two means. The first thing is, a lot of people do it by electron beam welding. So using the electron beam, you just forcibly do a coating on the top of it, and then the particles are being projected by a plasma torch. A plasma is a fourth stage of material, as we know, where what we use is, we raise the temperature all the way up to almost about 15,000 to 17,000 degrees centigrade. The materials are melted at that moment, and then the particles splat by splat are deposited. Zirconium, oxide plus yttria. Yttria is used as a stabilizing material because at 1000 degrees centigrade the phase of zirconia changes to tetragranule, which is destructive and it breaks. We do have on the top of this, in this, certain amount of cracks which are technically being created so that the expansion contraction is taking place and they do not peel off. The bond strengths that are achieved are in almost excess of 8000 psi, which are adequate for this purpose. Right. So, anything further you would like to ask me about? No, actually, it's these are the particles are straightway. It's not grown. No, it is deposition. It is a deposition. It's not grown within the base material. It's not grown within the base material.
Everybody understands, right? So I don't know if I have a picture of it, but if you look at the cross section like this, so what Rakesh is saying is, so there is your bond coat. I'm going to exaggerate everything. So there is your bond coat, which is microwave, right? And there is a little TGO here that I keep seeing on the pictures.
Instead of saying as technically
and
grown,
and then you got your top coat.
No, this is not TGO. It's actually thermal barrier (TBC).
Right. The whole thing is a TBC.
Basically a TBC, a thermal barrier coating, because the particles are deposited on a layer-to-layer basis. It's not grown from something else inside.
So there is your top coat, YSZ. I mean,
yeah.
Or it could be something else too.
No, technically only this is most preferred, except for the MIG and those planes where they use many different types of calcium oxides and those things. So this is different.
And here is your nickel alloy.
Yeah.
Here is your nickel alloy.
See, let us understand the function of it. The function is to see that the temperature that reaches the base material is lower. I mean, it reduces the temperature here.
Yeah. So how much did you say?
232 maximum.
So from here to there is a 232 temperature
degree gradient.
So there is a. So this is your delta T.
Delta T.
Okay. Yeah. So, but the thermal expansion could be happening like this also, right?
Yes.
Right?
Yeah.
Thermal fatigue.
Correct.
Yeah. So did you say you intentionally put cracks?
Yes, you intentionally put cracks except for the M-Crowley layer where there are no cracks.
Okay, but here.
See, let's understand one thing.
Yeah.
Once the oxide has already formed, this is oxygen transparent. That means it is only the M-Crowley layer which is able to take the oxidation that takes place at a high temperature. So that is why this layer does not have cracks, while this definitely has cracks. Certain amount of cracks which are...
You do that intentionally?
Yes. Porosities or cracks are created within the coating. All the way up to 15% at times.
Okay, 15%. Okay. Because of this thermal fatigue, the coating, there's no load here. Irrespective of the load, the temperature gradients, even this way there's a temperature gradient. I think we were talking during break time. This is seeing your flue, the combustion gases.
Yeah, they are flowing this way or this way.
Or this way. And this is your base to the disk. So this is cooler, this is hotter, very hot. And there's a gradient here. So there's always a thermal fatigue going on. So the coating can come off if the thermal fatigue is too much.
Yes.
Therefore, the adhesive strength has to be.
And yeah, adhesive strength is very good and that is being created. And second thing, the CTE has to be balanced. So that the grade, and even at the expansion that takes place, and the coefficient of thermal expansion matches all the way up to this extent.
So so that's your delta E alpha, right? Is your thermal strength.
Yes.
It's a function of, I don't remember exactly, but it's a function of the modulus difference
and the
thermal expansion coefficient,
yes,
and the temperature gradient.
Absolutely.
Right?
Yes.
So that what will give rise to thermal strength.
The basic purpose is to see that the strength is retained and you are able to raise the temperature inside an engine so that there is more fuel efficiency.
So how long does this coating last?
There are scheduled maintenance, but approximately 6,000 hours is accepted practice. 2000 hours is the checkup point, and 6000 hours is after which the coatings are peeled off and recoated. No, these are for all our jet turbines. Every, whether it's Pratt & Whitney engine or it's a Rolls-Royce engine, they are all coated by thermal barrier coating. That's compulsory.
When do you repair the coating? When do you change the coating?
Every 2000 hours there is a scheduled maintenance. Even in case of a failure, the engine, you will suddenly feel a loss of power, nothing more than that. So at that time they cut off the amount of fuel that goes into it, and then they land and then they do the complete maintenance part of it. But even if it gets spilled off, there is no issue in terms. There is no immediate danger to life as far as the flight is concerned.
So what is the type of inspection on the surface?
They remove the part, they check it up every 2000 hours, and then they conduct a small flight test. I might have a photograph of it, but yes, they conduct there is a rig on which the engine is mounted, and they take the full pressure part of it. If they see that there is a temperature, they measure the temperature of this, and they see that there is still a temperature barrier available, they consider that the coating is fit enough to use. Or there are methods of checking the coating also. There are many coating thickness gauges available, not an issue at all. No, these are technically not grown. These are deposits. This is actually a deposition. Manipulating the equipment, robotics, controlling the flow of the powder, controlling the temperature at which the flame is being generated, everything is precisely controlled, and that is how you maintain a TBC coating thing. And each layer thickness is 25 microns. So anyway, you have a control of 25 microns at any given moment of time. You can actually see it if you want. We do the coatings, and you can see how we control it using robotics. Just a few kilometers away from here. Not difficult to have a look at it.
Fantastic, great. So we don't use any of the components coating that Rakesh is talking about.
Yeah, and
especially the turbine, the combustion liners, combustion.
There are two places where the coating is done. One is this, and second is on the blade part of it. Yeah. We have got clearance control coatings.
The turbine blades.
No, here you have got a clearance control coatings, where the grooves are cut by using the powder deposition on the top of it, so there is no gap. Otherwise, you don't get that 1:30 ratio of compression. That's how it's being done.
It's one of the most complex engines. Turbine engine is so complex. The day you will make the turbine engines, imagine that
yes.
You are the high. Thank you so much. I don't know how to thank you.
Oh,
that was wonderful. Very good. Thank you so much. So, so I'm glad that Rakesh introduced us to, to the coatings, because I don't have to anymore. Like I said, we don't use any material, even for the aircraft. A lot of times we don't use any materials without short peening, right? So that we introduce the residual stresses to increase the fatigue life. All aircraft parts, most of them, when I say all, landing gears, wing, fuselage, they all have to be short peened so that we have a better fatigue life. And here, they're all thermal barrier coatings. There, they are corrosion protection coatings and fatigue life extension coatings, but here is all thermal barrier. The more you can push the temperature of operation, the more the efficiency, as he was talking about. And the only way you can do that is by putting the turbine TBCs. So if you demonstrate that you're a good student, maybe he'll hire you. Maybe he will, train you. This is a great technology. Yes. Oh, you were just going to ask some question, or no? Are you going to ask a question? Okay. Yeah. You were just raising. Okay. Yeah, this is the second time he has done. I always think he's asking a question. That's okay. I don't mean to embarrass you. Yeah.
See, sir,
huh?
crack propagation the coating,
Oh.
crack propagation the base material. Suppose initiation short of the coating. Both are having elastic models, different elastic models. Base material will have different elastic models.
Okay. Big question. I don't know if I can answer the whole question. I can only tell you what I've experienced. A lot of times we will have FOD, foreign object damage, which will hit the blade and make a little bit of notch, okay? And that's a starting point for a crack to form. But as Rakesh just said, every 2,000 hours, they have to check the coatings. So if the coating comes off because of the thermal fatigue or some other reason, maybe because it was not deposited properly, but that doesn't usually happen because most of the people are very dedicated in this business. So if the temperature, for any reason, if the throttle of the engine goes up, higher throttle, maybe much more temperature is experienced higher than the specification, then you can start a little bit of losing the coating, but not forming a crack. Yeah.
Like a belts hitting the air tops.
Yeah.
It may affect the coating of the turbine.
Yeah, but it will be more of a damage to the blade itself. Yeah, blade itself at the edge. You know, the leading edge will take a hit. The trailing edge is pretty thick actually. The leading edge of every blade is every blade has got a leading edge. Just like your wings, leading edge, when you go aft, it's you know, right? It gets thicker. The same way the blades are also. So if a foreign object damage takes place at the leading edge, then you can have a notch. And if you remember, the stress concentration factor that we derived in the class was 2 times square root of A divided by rho. Yeah, it gets amplified. Yeah.
So that is not going to affect the base metal.
It will if it's a through crack, yes, right? Yeah.
If possibility to have it.
Yeah, if it's a through crack, it will. A lot of times the crack can be through crack or it could be a surface crack. If it's a through crack, you better watch it. Yes, sir. Yeah. 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 So there you go. They have the answer. Yeah.
Columbia spacecraft.
You're talking about 2 things now. Okay. Yeah.
Same country. Crack propagation happens only the coating Columbia Air spacecraft. The collapse is entitled place only because of the coating. Maybe.
Which you're talking about Columbia?
Columbia space.
It peeled up.
That is, the coating has peeled up. It has fallen over the period of time. That only resulted in the collapse.
I'm trying to recall the Columbia accident. Okay.
There is a very much important case of crack propagation. Even though it is not.
Was there a coating? Yeah. Not a coating. Yeah, I don't think so. Yeah. Yeah. Oh, that is different. Yeah. Ceramic tile, that's different totally. Ceramic tile is a thick one. Yeah.
Which is used in aerospace.
Yeah.
When it goes in the satellite,
Yeah.
etc.
I have seen a lot of space shuttles after they came back to the Kennedy Air Force, to the Kennedy. So we used to go there and look at they will give us an opportunity to look at the whole space shuttle. There are little dents everywhere because of the particles in the space. They keep hitting at 300,000 miles per hour. You know, so you'll see a lot of those dents, but that's pretty normal. Nothing happens. Nothing happens. But in that case, yeah, because space shuttle is nothing but an aluminum airplane onto which you have deposited the ceramic shields. I mean, I'm oversimplifying it, but that's what it is. With in between the ceramic shields, you got these rubber, you know, washers. That's, you know, very simplistically put in, right? If one of them comes down, you're basically going and seeing the aluminum now. You're screwed. You know, aluminum cannot take anything more than 300 degrees F Fahrenheit, 150 degrees C. It cannot experience more than 5 minutes or so. It will burn up. Yeah. Okay. So that's a good lecture on. It's always easy to work with the base material. It's much more difficult to deal with the coatings actually, you know. But we just saw the coatings, and we will talk about the non-destructive inspection of some of these things, you know, non-destructive inspection of coatings, even thermal protection tiles. I did some work on thermal protection tiles actually in my lab. using scanning acoustic methodology. So we'll talk about some of the work that I have done personally. There are some things I'm not aware of, okay? So let's see. So here is before I show this, let me show you, it's not arranged properly because I was not knowing as to how we will. So this is how the technology developed, right? This is how the technology developed in terms of materials for resistance to creep. Very early on, this was the material that we used to work with, equiax grains. So these blades were made up of equiax grains. See, that's a magnification of this one here. Then after some more years, we moved to directionally solidified materials. So here you have grain boundaries. Obviously, this is a grain boundary that is perpendicular to the stress axis. In the temperature regime where this operates, you get into that creep. You get into the vacancies going along the grain boundary and causing the grain boundary cracks, right? We showed that in the creep chapter, right? Okay. So the idea was to let us take away these grain boundaries that are perpendicular to the stress axis, right? Because in order to form a crack, your stress should be at like, if it's 90 degrees, it's going to happen. Cracking is going to happen, right? So the idea was to make the boundaries parallel to the stress axis. That way, the boundaries won't see any stress because now it's parallel to the stress axis, right? So that is the directionally solidified structure. So all the grains that you are growing in the cast structure are all columnar grains, okay? So the grain boundary, so look at this creep. You have moved from here to there, and the length of the directionally solidified material will last for much longer time. So then the idea was, hey, take the grain boundaries out totally. Single grain, one grain only. So single crystal. Single crystal means no grain boundaries, right? So then we moved the technology to single crystal. So you can see the improvements, how they took place. But that does not mean that we don't use this till today. We do use these things. We do use these. We do these use also, like Patton Whitney, 1480, 1484, CMSRX. Every company has got their own names. Rene 95, PW 1484, CMSRX. Single crystals. We do have single crystals made by each company now. Okay? But I wanted to show you this, how the technology has evolved. Better and better and better crack growth resistance, because creep happens to be one of the driving design parameters, right? So just imagine for a second, right? Just imagine I think I drew this figure below, but I will draw it one more time. This is going to be a cartoon. So there is my turbine disk. Of course, you got all these roots, right? I'm just going to draw like this, and there is my bore in which my shaft is going. Shaft of the engine is going through this, right? So this is my bore of the disk, and my blades are here, right? I'm just going to draw a blade like that, but so there are like rows of blades here, okay? So this is my leading edge. This is my trailing edge. Okay. So when we were talking about foreign object damage, it's not going to happen in the turbine. That's way inside the engine. If you pick up a fastener or something like that, it will probably come up to the fan, maybe through the compressor at the most, first, second, third stages. But going to the turbine is almost very difficult because you've got a lot of places to travel through. So here the temperature is the lowest compared to the temperature here, right? The temperature keeps on increasing. This is almost, again, relatively, when I said low temperature, again, low temperature in a relative fashion, right? So there is my bore, and there is my rim of the blade. There is my rim for the disc, and there is my blade tip of the blade. and there is my root of the blade. And this is the chord of the blade. CH. So these are all the definitions. Because if you have a blade that has come to you for investigation as to what happened to it, then you'll say, okay, at this, maybe 3 inches from there, from the top, that's where the damage took place, or here the coating came off, this much distance and all that, right? You have to tell exactly where everything took. So why did I draw this? The reason I drew this is because this is revolving at 10,000 RPM or even 30,000 RPM, depending on which engine you're talking about. So the centrifugal force is acting that way. This blade is trying to come out of the turbine disc actually. That's how much is the force, okay? This force is extremely large. I cannot tell you in newtons how much it is, but it's almost like holding on a truck, basically that's how much it is. So the design of this thing really gets complicated. So because of this centrifugal force acting this way, and the high temperature, your creep becomes a very important design factor for your blade. And the blades usually are made by casting. We don't even do just casting, investment casting, okay? So I just drew something, just nothing specific, but just trying to show you approximately the stress. This is a log scale, just about 300 MPa, okay? And minimum creep rate. So there is your small grain, there is your coarse grain. We already saw this. Big grains are good for creep, small grains are not good for creep. So much faster crack growth rate, creep rate in the small grain one, right? Okay. So here is a cast structure of a blade, and I like the MAR M247. There's a reason why I had to learn about MAR M247, and okay. So anyways, there is the MAR M247 cast structure. The pouring temperature was 1,360 degrees Celsius, which resulted in a grain size of 70 microns. If you look at these grains, they're just about 70 microns on the average, right? And then this is the microstructure after heat treatment. Too bad I didn't put the temperature down for the heat treatment, okay? So here are some pores, okay? This is before hipping. This is before hipping. This is after hipping. Before hipping, some of these pore structures, this is a pore, that's a pore. Sometimes it gets difficult to decide if it's a pore or is it an intermetallic particle. So after you do your optical microscopy, take it to the SCM and do the energy dispersive X-ray analysis so that you will make sure that it's not a pore. Huh? You can also do that, okay? NDT? Okay, yeah. NDT, but that has to be... You do, but what do you do? CT X-ray. CT, right? CT will give you. CT X-ray will give you pore. Yeah, not the regular radiography, huh? No, radiography will give you X-ray radiography. Will give you the porosity. Okay. So if the porosity is big, it's a large size, then you can do X-ray radiography. But if it's small, you may have to do X-ray radiography, much more precise one. There's a CT, computer tomography you can do, which is becoming more and more common. Every laboratory is trying to do that now. You can get a better numbers, smaller number also. But you can see that if you do the hipping, there's a big change in the porosity. Again, you're not taking one picture, you're taking big statistical pictures, okay? Because every time you look, you're only looking at 10 microns, and that's not enough for a big, if your blade is this big, width of the blade is this, and you're looking at something like that, you probably want to, not every blade will be, I don't know if every blade will be checked, but this is something you can do. And this is gamma prime. I didn't convert it to symbol. This G prime is gamma prime. Gamma prime before and after. Not much change in the gamma prime, okay? Because the hipping temperature, the stress is usually very low in the hipping, 10 to 15 MPa, maybe 24 hours time. Okay, so that's just a brief description of the microstructure, of the microstructural characteristics that you should be thinking about when you're looking at cast structure for a blade. Now, MAR M247, the one that's exactly in competition with this is Inconel 713. Okay, so compare and contrast between the differences between the two. I put here another picture just to kind of show you. Nice dendritic structure you can see. Can everybody see the dendrites? If you want to see better than this, you make this is the top, this is looking down. If you make a section this way, so you can look this way. So if your growth is this way, bottom to top, you're better off looking this way. Then you'll get the real structure of the dendrites. Real structure of the dendrites, which is, right? This is your primary dendrite. And this is secondary arm, right? Okay, and you can have a tertiary arm too sometimes. So primary, secondary, tertiary. And you can put whatever you want to afterwards, okay? So if so in a wrought material, we will break these dendrites down. But for a blade, we don't have to, because the technology is very, very robust. It's very well solidified. It's a good technology where we are very sure that we can just do the casting of the blades, wax molding, wax molds. So here, see, you can see this one. I don't know how to make those PowerPoints. When you click, the second picture shows up. I'm not that good at, maybe one of you young people can show me. Because I wish I could have made this bigger to appreciate the junk, the damage that's there on this before hipping. And then after hipping, it looks much, much better. I don't know if you can see it from there. And there is the composition of MAR M247, 8.37 chromium, 10 cobalt almost, tungsten, molybdenum, aluminum, titanium, tantalum. Geez, it goes on and on. 1.5 hafnium. So we're going to have a lecture by, I think, is Amit here? Yeah. Maybe a lecture from Dr. Paliwal, right? At some point, Professor Paliwal is going to come and demonstrate if we put all these components into nickel, what kind of phases can we predict? He has developed his own software now. Thermocalc is one, but he's got his own software that he can do the prediction, which is great. Who is that zirconium-based glass guy? Zirconium-based glass. You're doing iron-based glass. Same thing. Okay, not same thing, sorry. Iron-based glass. Yeah, I'm thinking of somebody else, zirconium. But he's doing iron-based glass, for instance, which is a multi-component alloy. How many components do you have? 7? 9. So he's got 9 elements. So he wants to know what phases are going to come or precipitate out and which are going to be stable, right? So he should be able to, maybe you should give that. Did you already give that example to Dr. Paliwal, Professor Paliwal? So when he comes, that will be a good example to see if it can predict those phases and the stability of those, right? That's what that software is supposed to do. Life is getting more complicated in this world, Okay. So interesting, right? So here is this is what delta epsilon p, okay. Again, don't worry about these curves. Only thing is that trends are important because they'll keep changing depend upon the specific alloy. All you want to know is what is the trend? Why is the trend like that? What are the microstructural attributes that are giving rise to the trend? That's all what you're interested in, right? Don't worry about the absolute values. For example, untreated, well, that means not hipped, at 900 degrees C is the red one. There, okay? This is a plastic strain amplitude. So low cycle fatigue, number of cycles to failure. This is a low cycle fatigue. So the stress that you applied was above the yield stress. Okay? So this is percent, 10 to the minus, let's take something, 10 to the minus 2. So this is point, or 2 times 10 to the minus 4. Am I right? 0.02%. Very small strain, okay? Very small strain. This 10 to the minus 3. So eventually what happens a lot of times in these materials is, in these tests, who can do low cycle fatigue in the lab right now? Anybody can do low cycle fatigue other than you? You guys are doing everything. Low cycle fatigue, Bharat Forge, low cycle fatigue. You can do low cycle fatigue. Yeah. So some people can do low cycle fatigue, but if you get an opportunity to do low cycle fatigue, okay, try to do that. I'm sure you will be able to do it IIT Gandhinagar sooner or later, some of your students, right? So the machines are coming, they're on their way. Right, Professor Arora? They're on their way. Yeah, they're on their way. So if you're doing, there is your sigma axis, there is your epsilon, right? And you're doing a low cycle fatigue. A lot of times when you apply these kind of low strains, you won't see the plasticity yet for quite a few cycles. The line will be basically be going elastic, back and forth, remaining pretty much elastic. But eventually what will happen is, it will break out of its elasticity. It will form a little loop like that. Little loop. And eventually that loop will get bigger. And then it will get saturated. So even a lot of times you can start with elastic. Only one line going up and down. And then it will go to the plastic regime. Okay? The point that, and here is a high cycle fatigue. You know, again, what's going on? So at 10 to the minus 2, yeah. So hipping gives you obviously a better number of cycles to failure, that's what you would expect. If your hipping is right, you should get a longer lifetime, right? Both in high cycle fatigue and in low cycle fatigue. That's all. I mean, that's all what you need to know. You don't have to worry about anything else. Before hipping, I don't think you can see, but the fatigue crack initiation, there is one initiation site right there. It's not very good. Maybe you can see better there. There is another site here, okay? Sometimes you can have multiple sites in fatigue crack initiation, many times, but only one of them will take over and go to the failure. I think I have a micrograph. I think I have something about that to talk today. After hipping, because you close down these casting defects, let's assume there are pores, big pores, or shrinkage that happens when you're casting. In the hipping, you remove them, you close them. The porosities have been closed because you got a pressure and temperature. Movement of atoms is taking place. So you close those guys. So the initiation site has now moved into the center almost. All the way from there to here. Good, interesting, right? Yeah.
Low cycle fatigue.
Ah.
What is the area under the curve indicates?
The area of the loop, it will be plastic and it will be hysteresis. That hysteresis loop is the plastic energy that you're putting into the material. Anytime you multiply the stress with strain, it's energy. So that loop that you're talking about, so this loop, so here, let us say from here to there, this one, this area is essentially the work that you put into the material. You can count the number of loops and you can see how much work you have put in.
But the stiffness degradation will be there. Stiffness,
Yeah. Not so much for metals. You're talking about composites, right? Yeah, the composites guys right there. So in composites, if you do a damage, the elastic modulus will go down. And you can tell, I don't know, is there a quantitative relationship Yeah, between the damage and the elastic modulus reduction. But in metals, the modulus doesn't change that easy. It's very difficult to change modulus in metals. Of course, temperature will change a little bit too much, high temperatures, but yeah. So that is the plastic energy.
In some cases, we used to evaluate the damping of material.
Yeah.
By studying this area.
Yeah, absolutely. Absolutely, yeah, absolutely. Yeah. Yeah.
But in free vibration, we are neglecting the damping, and we are only concentrated on the frequency.
In the
Free vibration.
vibration. So if you take those blades, for instance, those blades that we were talking about, those blades are also vibrating like this. Not only they are being pulled like this by centrifugal force, but they also have a vibration frequency too.
I think this is forced vibration. It is major role impact on the damping property.
Sure, absolutely. Yeah, there was a failure like that one time, damping of the turbine blades so that you reduce the fracture probability.
Yes, sir.
Because there will be resonance, right?
Yes, sir.
The resonant point where it is, the node, that will be the point where a failure will take place, right? Yeah.
The resonance frequency coincide with the excited frequency, sir. Excited frequency.
That is actually one of the non-destructive evaluation methods you're just talking about.
I am using, sir.
You're using that method? Okay. Very good.
By past years, that's a technique method.
Right.
We can put damping software.
Okay. Very good. Yeah. So what he's talking about is this. If I have a blade, or if I have even a bar, a beam, for instance. Yeah, even if you take a beam, if you measure the resonance, that means if you put a ultrasonic or even a sound wave, it will go to the end and it will come back. And it will have the resonant points, right? If you now damage the beam, if you put a small crack and pass the same frequency, same waves, it will be behaving completely different because you put the damage in there. So that becomes a non-destructive evaluation technique of measuring the resonant frequency essentially because it's changing. Like if you, for instance, if you take a truck, for instance, okay, if you drive your truck in mud all the time, so when you're driving on the streets, your axle will have a certain resonant frequency. But let us say you're about to break your axle, that connects the two wheels, for instance, going like this up and down on the mud or the mountains or whatever, and if you put a small crack in it, and if you had a non-destructive evaluation sensor to measure this vibration frequency changes, then you can tell that there's a crack that has formed because it will pick up. As a matter of fact, that's a patent of one of my friends who's selling that technology to a lot of guys in the army trucks. What do you say, huh? Chaudhary Saab and also Rahul, right? You guys don't use that? Well, in the Air Force, you guys are Air Force. But the army trucks that come into the cargo planes,
What is the smallest size of crack you can detect?
What is the crack size that it can detect? I don't know. I can look up. The guy's name is Adams. Last name. First name is Douglas. Yeah. Look up the patent, Okay, so that is so much about that. So again here, creep of Marham 247 casting, okay? Because we just talked about how the centrifugal force pulls the pulls the blade out. So that is your stress. It is under temperature. So the creep would take place, right? So this alloy is a 60% volume fraction of gamma prime. Remember when I was talking about yields changing with temperature, the example that I gave was 20% gamma prime. Here is a good example of a high volume fraction, 60%, okay, of gamma prime precipitates, okay, in a disordered phase net cubic matrix. That's fine. Excellent castability and high temperature properties. It has been shown over and over that this material is castable. That's the important thing, right? Okay. It has been tested up to 982 degrees Celsius. But the important thing would be that I'm missing here is for how long. Whenever it comes to high temperature applications, you need two things. If somebody says, hey, my alloy goes very high to 982, for how long? That becomes a question mark, right? I don't have it here. Okay, so that's all fine. So you were talking about precipitates. Okay, you were talking about something like this. Grain boundary, so this is after creep, okay? After creep. Grain boundary cracks, primary gamma prime, secondary gamma prime, and look at the rafting. So this is your original microstructure. This is your microstructure afterwards. In superalloys, what happens is these precipitates, okay, these are primary gamma prime, secondary gamma prime. These big guys, they can stretch out like this, like rafts, like boat rafts. So this is called as rafting. So if you get a blade for failure analysis, you can cut the blade and look at the microstructure. If you see a microstructure like this, you can tell exactly what is the temperature that that blade got exposed to. You will be able to tell that. Many of the engine companies have a table, they call it as lookup tables. The size of this microstructural features versus the temperature. They'll be able to tell, okay? Because once this microstructure goes here, the blade is useless. The substrate material is useless, okay? Because it's lost its strengthening, it's lost its precipitation hardening property. I mean, the strength is not able to get from precipitation hardening anymore because these particles have become rafts. They are not able to provide you the strength anymore. So it's becoming like almost useless. You never want your blade to go to this situation, right? So I have a picture here, slide here. I think I thought I had, let me see. Creep. Okay, shoot. Okay, I don't have that particular shoot. I thought I had. It'll be nice to have, if I had the slide that showed what is the creep time for all of this, it would be nice, but unfortunately I don't have that right now. I thought I did have it. So, people are constantly, especially the Japanese, they're always constantly playing with how to improve creep in superalloys. These guys are very dedicated researchers. I was there for 3 years in Japan. They're unbelievable. They have creep machines still running from 50 years ago. Somebody started this experiment in NIST, National Institute of Standards and Technology, or NIMS, not NIST, NIMS, National Institute of Material Science. Somebody started the creep experiment in a big, they have this whole thing like a big football field, like a soccer field, big, creep machine after creep machine after creep machine. And somebody started creep test 50 years ago, and it's still running. Yeah. So if I started something and I die tomorrow, somebody else will take over and will run the test. Keep on running the test. So they have data of actual data that is being from real life, from real data of creep. They're not extrapolating data. These guys are unbelievable. They hold like hundreds of machines, So this is the Harada guy, the boss, he's the boss at NIMS. I mean, boss means in a technical boss. He's a very smart guy, And, different editions of rhenium. Different editions. So 1 and 3 atomic percent of rhenium added to MARM 247 increases, makes it better. If you add rhenium to this, 1%, 1 atomic percent, 3 atomic percent, the creep gets better. But anything more than that, it brings back here. It makes it worse. The situation reverses. So they have good data here, actually. I put here tensile strength, ultimate tensile strength, and all that. Huh? I already showed this, okay. I put a bunch of alloys here, which I'm not going to talk about. So this is the combustion materials, okay, alloys that are normally used, Haste alloy, Nimonic, 617 and 230. And you were mentioning some alloy during the break. X750, right? Yeah, X750. So we should look up that one. Bunch of turbine blade materials. I mean, there are so many of them. Superalloy discs, you know, iron 718, the workhorse alloy. And then some people are going back and looking this iron 100 again. It's a powder metallurgy superalloy, powder metallurgy. This has been developed and has been around for quite some time. But they're looking at, again, at, you know, what is this alloy all about? They have a feeling that this alloy may be very good again for disc superalloys. So they're looking at this again, A286. Merle is a NASA alloy, nickel-based powder metallurgy route. Yeah, there are so many alloys, but you need to know the basic principles because it's impossible to remember these things. You need to know the basic principles. If I don't, I'm not going to bore you, but I want to just repeat some of the important things. Solid solution hardening, grain size strengthening, super solvers, sub solvers. What is the effect on fatigue? What is the effect on low cycle fatigue? What is the effect on fatigue crack growth? What are the defects in castings? How can we close up those defects? And as you know, Dr. Rakesh talked about, these coatings, for instance, the base metal, the microly, M stands for metal, okay? We use nickel, nicroly, Ni, chromium, aluminum, yttrium. And then, you know, the thermally grown oxide is not a big deal. Apparently it's there. By default, it's there. And this yttria stabilized zirconia is one of the top coats. And that's what is being used by him. So some of these things are important to remember. These are the important things to remember. Okay, and these are not very thick coatings. They're very, very thin coatings. You know, very few, couple of hundred microns, maybe even less, maybe. I can tell you in inches, but I don't know about microns. Okay. I have to come over there. I can. Yeah. Tensile properties? Fracture toughness? Toughness or just fracture? You know, I haven't seen a whole lot of emphasis on fracture toughness for the nickel-based superalloys. Yeah. I've not seen much. So it looks to me like fracture toughness is more of a secondary property. Fatigue crack growth, creep, tensile properties are the ones that I've seen most of the time. Nobody seems to worry about, and then, yeah, high cycle fatigue, low cycle fatigue, you know. I have heard, I'm not sure about it. Again, some of these things you have to find out from people who are more experienced. I heard that a turbine disc, for instance, expands the very first cycle that you turn the cycle on. But afterwards, it's nothing. The first cycle is the most important cycle. You know, I don't know. I mean, that's what happens or not, but that's what I heard. You know, maybe some of these people who work hands-on every day, but that's something I heard from one of the guys. Okay. I want to show you, again, another example of, I'm also looking into this IN 713, MARM 247 and Inconel 713, cast and hip. You can see that this casting defects there. I want to show you one date on fatigue crack initiation. We talked about this already. Before I show you this, this is what I wanted to show you. Of course, I never completed this. This is the SN diagram for CMSX, different, and then, you know, PWA 1484, single crystal of Pratt & Whitney. You can see here 10 to the 10, high cycle fatigue. This is where we used to stop before. This is where we used to stop, 10 to the 6. Now that's where we start because we got ultrasonic fatigue machines. 20 kilohertz per second, right? So we can do very long frequency because they matter for the engines because of the number of cycles we put in every second. So people are doing more and more tests at 10, that will take them to 10 to the 10 cycles per second. You can see how this curve has gone down for this CMSX4. Okay, just imagine you start the test right about there. That is 10 to the 8. Just imagine, completely wrong number. You can go down, it goes down all the way. Right? So very high cycle fatigue using ultrasonic machines, ultrasound machines.
So continuously,
Huh?
endurance limit of
Yeah, absolutely.
still have to perform the
Yeah, you don't have to worry for this for the aircraft materials so much, but for the engine materials, you do have to worry about it. Yeah.
We have to 20 power minus 10 cycle. It's no endurance limit.
Yeah.
Still we can use it for the use of
Yeah.
then only we can get it.
Yeah.
This is half the building. Because the endurance limit is not distinct.
Yeah. Yeah.
Normally
Right.
supposed to
Right.
be 20 power 6, but it has gone to 20 power 10. Even then, that limit is not.
Right.
It is almost a straight line.
Straight.
Yeah. It is almost straight line. Yeah. There has been a lot of work that was going on in this area now. I've not looked at it carefully yet. Okay. Okay. Again, another defect in their high cycle fatigue. Yeah, comparison at 20 hertz and 20 kilohertz. This is all kinds of stuff. It all depends on what you want to do. Okay. I want to show you one more important thing. Before I go somewhere else, let me show you this. I don't want to forget this. Yeah, Kitagawa-Takahashi diagram. Okay, I'm going to simplify this very, very much. It's a you know about this very much, right? Yeah, Takahashi-Kitagawa diagram. So this is how we used to do analysis before. Okay, we still do. So basically, here I'm plotting delta sigma alternating stress on a fatigue sample. And here is my K. Actually, I don't know why there is CL there. That's okay, K. So there is your endurance limit. And there is, that's the way this is your crack growth curve. And here is your high cycle fatigue data. Okay? So if you're in this regime, non-propagating cracks. Okay? This is more scientific. But yeah, it's scientific, but I'm going to, there's an important thing that comes out of it. So non-propagating cracks. The way we have understood non-propagating cracks all this time is, like we were talking about endurance limit. If you're below the endurance limit, safe region, no propagation of cracks, right? No propagation of the cracks. If you're below the fatigue crack threshold, no propagation of the cracks, because it's a fatigue crack threshold, remember? Log DADN, delta K threshold. The curve comes down like this. Below this, no crack propagation, right? So if you plotted this, if you plotted those things, you will end up with non-propagating cracks. And somebody was asking the other day, I don't know who it is, but they're saying, we formed, sometimes you, I think, right? Yeah, I think you were asking. There are a bunch of cracks sometimes. One crack does the failure, but the remaining cracks are still there. There are secondary cracks. We call them as secondary cracks. We call them as non-propagating cracks. Was it you? No? Come on, yeah. Somebody, one of you guys were there, were asking. You? Rahul? No. No? Oh, yeah. Probably you were asking. Non-propagating cracks? Secondary cracks? Okay, anyways. So the point was, okay, this is something that's going on. There's a crack there, there's a crack there, there's a crack there. But there's one crack that leads to failure, but the remaining cracks just stay there. Like we see multiple crack initiation sites, but out of that, one of them leads to failure, and there are some that do not lead to failure. They are non-propagating cracks. Okay? So what these guys are talking about, Sadananda and those guys, They've been working on this thing for about 10, 15 years now, maybe 15 years. So this is one of the things that lately they have produced. Modified thing. Without looking at all that stuff, I'm going to tell you this thing. They are saying that, which makes sense actually, but so what? Okay, so here is my component. There are some cracks, and there is a major crack that leads to failure. Okay, what they're saying is that, so when this crack was small, let us say this crack was small, in front of every crack, these cracks have to overcome internal stresses. These cracks have to overcome internal stresses, okay? And those internal stresses are very unique to those cracks. Unless they overcome these internal cracks, they won't be able to propagate. That's why you're sometimes left out with non-propagating cracks. So this internal stress also has to be added to the applied stress, essentially. So this is one of those modified Kitagawa-Takahashi diagram. So all they have done is to introduce this internal stress. Okay. And that's a function of many, many things, residual stresses, dislocations, and all this stuff. Okay. That's one thing I wanted to show you, because a lot of people, there are many, many papers they have published recently, about 10, 15 papers on this whole concept. And some people embrace it, some people don't. Because from a practical point of view, I hate to say that to my good friends Sadananda and Vasu, that nobody's going to embrace it. Because from a practical point of view, I'm not so interested in internal stresses and all that. If I'm in the maintenance business, I don't really care about all this stuff. My most important parameter is K and DADN, that's all, right? When is the crack going to become unstable? And that's what I'm interested in, right? Okay, so you remember we were talking about small cracks. So when these cracks, where was that picture? Yeah. There have been many works also done here. Let me put this crack, okay, like this. This is a long crack, this one. And these are microstructurally short, they're small cracks, okay? They're small cracks. What is meant by small? They're probably smaller than the grain size of the material. These are probably several grain size of the material. That's how we distinguish, in a first order, that's how we distinguish between short cracks and long cracks. When people started to do short crack research, they found the data to be like this. So if you did not know enough about short cracks, you are getting a data here, which is this, but at the same time, if you have a short crack, you're getting about 2 orders of magnitude faster. So people became all excited, saying, wow, short cracks don't obey delta K and all that stuff. They need a different type of a theoretical mechanism and all that. Because really, see, here the cracks are not supposed to propagate. This is a threshold. Cracks are not supposed to propagate below this. Here in this regime, they're not supposed to propagate. So if you took a compact tension sample, if you put a pre-fatigue crack, and if you did a normal experiment like you normally do, you find this threshold. The reason we call it as a threshold is because anything less than this delta K is not able to drive the crack anymore, right? But if you take a smooth bar and if you put a little notch in it, like a thumbnail notch, just exactly like this, small crack, and if you now watch that crack growth and get the DADN, crack growth rate, what you're finding is there is no threshold, but it keeps going up. Very bizarre, right? So people start to think, well, the K is not applied, there should be some other analysis and all that stuff. These guys started to say that these microstructurally short cracks, they still obey fracture mechanics, but there is an internal stress, localized internal stress regime that has to be overcome. And they have explained all this stuff, why the short cracks behave like that, and there is nothing peculiar about it. Remember I talked about crack closure, just briefly? If this is your delta K, if this is the delta K, and this is my delta closure from here to here, then the crack is effectively seeing this is delta K, right? Because the crack does not close completely when the cycle comes, when the fatigue cycle is coming down. Let me take my time here, I'm rushing. We got a lot of time. There is my fatigue cycle. There is my compliance curve. We talked about that, right? And here is the crack surface. I'm exaggerating it. So that's my top part of the surface of the crack, bottom surface of the crack. So when I'm going up in cycle, in the positive regime, the crack opens because I'm going in the tensile mode. I'm going in the tensile mode. And at that point, this curve, my load curve is, let us say it's there. So this one belongs there, and this one is here. Okay? But when I'm coming down in this cycle, let me get fancy here. Oh, let me get a little fancy. So when I'm coming down in the cycle, I'm bringing down the crack to, it's going to get closed, right? Because I'm bringing down the load. Here's my specimen. Bringing down the load. The crack is closing. But what we said is the top surface and the bottom surface don't fit exactly, because these crack surfaces have got teeth of their own. They don't match up. They don't match up when you bring them down. So this curve, when you're bringing it down, it kind of stops there. It doesn't come back to zero because they're a little bit displaced, the bottom and the top surface roughness. So effectively, the crack is only seeing that one. So if you call this as delta K closure, the total delta K is equal to delta K effective plus delta K closure. If you're applying 10 MPa square root meters, this is 8 and that's 2, then what we're saying is, even though you're applying 10, the crack is only seeing 8, because this 2 is this 2, the delta K closure, because they're not matching up completely. The surfaces are rough. They don't match up. If you took an atomic force microscope, you can exactly measure the surface roughness, right? How many of you used atomic force microscope? Okay, try to use an atomic force microscope. Take some time from, I don't mean to put him in trouble. Call DMRL and tell him I'm coming over to use your atomic force microscope.
So my question is, this effect exposure will be more effective during short fatigue crack.
During fatigue crack growth?
Short crack. Short fatigue crack growth.
Yeah. No, even long fatigue crack growth too. As a matter of fact, I hate to say that, but is it off? Rob Ritchie made his career out of crack closure. He's published hundreds of papers just based on this crack closure. And the Sadanandas, those guys don't agree with it. They say, hey, crack closure is just mechanistic interpretation, which may be true, but that's not the whole explanation. There is an internal stress that needs to be considered properly. Now you can turn it on. That needs to be considered properly, you know. So, yeah. Yeah, so they're using replicas. They're using replicas. So each time they'll stop the machine, they'll take a replica, take it to the microscope and measure the crack length. Run some more cycles, put the replica. You know, replica is like a plastic tape that they'll put in front of the crack tip with acetone. They would leave it there. That will form an imprint. You take it out, it dries up in a few minutes, 5 minutes or so, and you take that to the microscope. And there is a little crack, you know, visible there on the replica. So you keep measuring that. It's a very painstaking thing. But people have done it. People have done it. But people are also using electric potential drop method now. And that's the data that's coming. And people initially thought, well, you're not doing the experiment right. Well, K is not obeying. You cannot explain it by K. But now, you know, the latest theory by these guys, Sadananda and those guys, is that that is real. It's got nothing to do with fracture mechanics. There is an internal stress that these cracks are not able to overcome. Okay? There's a lot of analysis to that. I'm just telling you the bottom line. You know, it's convincing, actually. It's quite convincing what these guys are saying. But the only thing is, it's not very practical. In this, practical from the point of view of maintenance guys. They don't care, you know. The engine guys say that, okay, the engine guys should be worried because their small cracks, they're very sensitive to small cracks. They cannot tolerate any cracks in the turbine engine. No, you're going to bring the engine down and you're going to bring the plane down. No, we can't take that. So they have, because of them, this has become a very serious research field for a long time. You know, so look at, now, if you're going by the long crack, you're saying there's no crack growth until 4 MPa square root meters, and here we're finding a very high crack growth rate at 0.9 or 0.8. That's a big difference. So what happens is initially the crack, so look at it the other way around. Initially the short crack, where do you start? Initially the short crack starts very high crack growth rate, and it becomes slower and slower and slower, and eventually it merges with the long crack. Right? So there is a small crack, very small crack. It's growing very fast, but as you keep cycling, the crack growth rate is decreasing actually, and then increasing again, and then picking up the long crack. As soon as it becomes long crack, there it is. So what they're saying is, this is happening, but nothing to worry about, as long as you're designing it for this delta K, the long crack threshold. As long as you're designing it here, you're okay. You know, this is just going to happen because small cracks behave that way because of this internal stress field. Okay, I just wanted to convey that to you, just in case you're thinking of, if you're thinking of, give me a second, please. If anybody is thinking of, like, you can take your friction stir welded samples in your case, and you can make a compact tension sample out of it. And if you're running a fatigue crack growth test, if there are residual stresses, if you don't remove them, you can see the effects of residual stresses on crack growth. Okay? And you can also see the fatigue crack growth after you remove residual stresses. Make comparisons. Okay? So, okay. So we talked about high cycle fatigue in cast materials, casting defects, and how it moves to the center after we're done hipping. Okay? We looked at crack growth a little bit, creep a little bit. Okay. Rafting, which is an important microstructure. Yeah. So let's stop here for now. Okay, let's stop here for now, and we'll pick it up later.
Okay, let me see if I can tell you a little bit about the material science department at IIT Gandhinagar. Okay, so we are in total 9 faculty members in the department. So my colleagues, we work on different areas. I work in materials processing, light metal alloys, welding, simulation, composites. And I have a colleague, Dr. Abhay Singh Gautam. He is a PhD from University of Virginia, postdoc from Berkeley, and he works on grain boundaries, materials interfaces. Professor Abhijit Mishra, he is a PhD from UIUC. He works on biomaterials, lipids, and then I have another colleague, Professor Emila Panda. She works on solar materials. She's a PhD from Max Planck Institute, Germany, and she works in the area of solar materials, thin film deposition, material oxidation kinetics, simulation of the oxidation process. Then we have Professor Manas Paliwal. Professor Paliwal is, you will be hearing from him. He is an authority on thermodynamic calculations. He is also a developer of CalFAT based software called Faxes, and we will have a live demonstration of the software here for you. Then we have Professor Superb Mishra. He is a PhD from Imperial College London, and he works on nanomaterials, nanotoxicity, bio-nanomaterials, and nanocomposites. And then we have visiting professor, Professor Jyoti Mukhopadhyay, who was the director of Aluminum Research Center in Nagpur, Jawaharlal Nehru Aluminum Research Center, and who is also a board member at Mishra Dhatu Nigam, and he's PhD from IIT Bombay. He is a very well respected person in the area of light metal alloys, aluminum alloys, and we will be having a lecture from him also on aluminum alloy status in India. Then we have Professor Surya Pratap Mehrotra, SP Mehrotra. He was a faculty at IIT Kanpur, and he's retired from IIT Kanpur. He's a visiting professor here, and Professor Mehrotra is an expert in mineral processing, extractive metallurgy, thermodynamics, kinetics. Basically, you name each and every part of metallurgy, he has worked in those areas. He has been working in the area of metallurgy for a long time. He was a director of National Metallurgical Lab, Jamshedpur, and he was also Metallurgist of the Year from IIM. And then we have Professor Ramchandran, who is a guest professor in the department. He visits us very often, so we are honored to have him as our colleague here. Amit, do we have the presentation? Okay, wait. Okay, so just to give you a small overview of what are the facilities which we have, I'll start with the central facilities, the electron microscopy. So we have a scanning electron microscope from GEOL. This is basically a FESEM facility which we have for the microscopic analysis. The features are we have possibility of doing platinum coating, and we can do primary sample presentation tools also. It has EDS attachment, so we can do SEM analysis and we can do EDS analysis both. The resolution is about 1 nanometer, 1.5 nanometer and 1 kV, and probe current is about 1 picoampere to 200 nanoampere. So that's the SEM which we have at central facility. You will take a look at this also. Then we have a confocal microscope, which basically is from TCS SP8 Leica. It has simultaneous multicolor resolution down to 140 nanometers. Live cell imaging is possible. So that's mostly for the biomaterials which we have. Then we have the ambient scanning probe microscope, also known as the AFM, atomic force microscope. It is good for the topographical analysis, electronic and magnetic properties analysis of particles and surfaces. Then we have an X-ray diffraction instrument available from Bruker. This is also part of CIF. So these 4 instruments are part of the central instrumentation facility, which is available in the campus. Then we have a basic metallography lab, which you can do abrasive cutoff, hot sample mounting, cold mounting. Now we also have a slow speed cutting machine also. And then we have grinding polishing instruments, which can be used for basic sample preparation. Then we have microscopes. We have stereo microscopes, regular microscope with camera attachment and software for grain size measurement, defect analysis and everything. So these are the microscopes which are available in metallography lab. Then we have the thermal characterization. So we have a TGA, which is from Perkin-Elmer. You can do temperature range up to 1000 degrees centigrade. Calibration is up to 200 degrees centigrade per minute heating rate. It can be connected with FTIR, so there is a hyphenation facility capability from FTIR. Then we have simultaneous thermal analyzers, STA. So basically it has a combination of TGA and DSC in a single instrument. Then we have a UV spectrometer. Did we miss DSC? No, there is a separate, there was a separate slide for DSC also. So we have a TGA, we have STA, and then we have a DSC, which is there. Then we have a UV spectrometer. You can look at the optical properties of the material. We have FTI spectroscopy, which can be used up to 8300 to 350 per centimeter wavelength. Then we have a microwave digester, which is basically to prepare the sample. The digester is there. Then we have a graphite furnace atomic absorption spectroscopy, which is also called AAS. So that's available. So these are all available in the characterization lab. Then we have heat treatment facility. We have a vertical tube furnace from Neighbortham. So basically you have a long sample which can be heated to a certain temperature, held on a certain temperature, and then can be quenched directly by dropping into a quenching media. So that's the vertical tube furnace which is available. Then we have high temperature furnaces up to 1550 degrees centigrade, different sizes, different temperatures available on different furnaces. Wait. Then we have another one is we have oven, which is you can keep your samples at a certain temperature for a long time. In terms of mechanical characterization, you have not added that one, right? So you can also go through this website. The website has all the facilities which we have listed here. So in mechanical properties, we have a torsion testing machine which can be used to test the torsion analysis, do the torsion analysis of material. Then we have impact testing machine. You can do toughness analysis, toughness measurement of the samples, CHAPI, IJOT, both. We have a DMA, dynamic mechanical analyzer, which is to be used for low strength samples, polymer samples for their dynamic mechanical analysis, load versus elongation analysis. Then we have hardness tester, we have hardness testing, we have Brinell hardness testing, Knoop hardness testing, we have Vickers hardness testing, we have Vickers micro hardness testing. All the hardness testing facilities are available, which some of which you will see today also. Then we have universal testing machine, we have 10 kilonewton universal testing machine, we have 10 ton and 20 ton two machines which we have for the universal testing. So you can do tensile testing, you can do compression testing, you can do 3-point bend testing, all the tests can be done here. Then we have nanomaterial characterization, we have the surface area analysis, BET surface area analysis. Then we have CPS instrument for the centrifugal sedimentation. We have dynamic light scattering and zeta potential analysis possible. And let me see, yeah. And then other than that, we have regular material processing facilities. We have a dedicated friction stir welding and processing machine also, which you will have a chance to look at. We also have in other departments, we have facilities related to particle size analysis, particle flow analysis, powder flow analysis and all that. So there are many facilities which are in other departments which we share with others. We also have, Mahesh, we also have corrosion analysis option, right? So we have electropolishing, we have corrosion analysis, corrosion cell possible. So these are some of the facilities which we have. So let's let's divide in two groups up to, Mahesh, you want to take it up? So first 20 names, group 1. We go to, I think, metallography lab. Second group can go to characterization lab.
All go to CIF. Let them from there split.
You want to go to CIF first or CIF last?
Then he can explain SEM and all. He will explain first. Then
Okay. So let's do one. Or I was thinking that metallography lab one group characterization, and then mechanical testing and FSW and CIF parallel. So let's do it this way. So we'll have 4 labs which we will cover: metallography lab, characterization lab, central facility and mechanical lab. So we'll have 2 groups. One group will go to one lab, another one will go to another lab, switch, and then the rest 2 labs. All right. Thank you.